So how are we gonna solve this? Well, we're gonna back up a little bit and think about a detail that we sort of neglected. In particular, we can think about traffic. You are not the only people on the road. There are other people on this road. Now, you can do what this is saying and solving the problem I was looking at by saying, okay, all of my U-flows, except for one of them, are becoming this obstruction. But this obstruction could be anything. It could be traffic. It could be other things you're carrying on these lines. They're all some arbitrary load, and we typically will use a little O there to say, this is the obstruction load rather than the load of the flows or something. So we want to minimize the utilization of the U flow. So let's say U of A plus load obstruction of A. We want to minimize that. Note, however, that this is not the same as minimizing this utilization and this utilization. We can imagine that if we had two arcs, and the load did 1 and the flow did 1, let's say that these are both capacity 1, then the utilization of the whole thing is the minimum of them, not the sum. In more complicated situations, there's a lot more there, but basically just know that utilization is, depending on where the loads are, is somewhere between the maximum of the utilization of those two things and the sum. So we want to minimize the utilization of this quantity. Now the thing is, we don't actually care what caused the obstruction. It could be traffic, it could be a temporary closure, it could be a whole bunch of things. We don't actually need to use any of that. So let's solve one of these obstructed network problems. The first we can do is we can say, well, we can't be any better than the obstruction itself, because flows are never negative, and if you add two things that are non-negative, it's the same or bigger. We can think about the space left over, the residual. There are quotes here because the residual might not be of the network unscaled. That's why we were talking about residual 4. But it's still a leftover space. If the network isn't big enough to handle the load, we can rescale the network in a particular way to get. So let's say an example. So right now we have these purple boxes that are showing some arbitrary load. This is in a flow, so I'm not using blue, and this is a network that we'll see again later. Well, if you took the residual right now, you'd start getting negatives. You'd get -5 here, -2 here. Clearly is not correct. But we can think about something related, which is, well, how much would we have to make these things bigger by to make it so we wouldn't get negatives? And it turns out the answer is multiplying everything by 4. Now, this does mean that the minimum utilization for whatever flow we put on here is 4, but just know that we want to do this so that the minimum is 0. So then we can take the difference and we're left with this residual with the yellow numbers. And this is what we're going to call the base network, N subscript B. And the base network is called that because if the utilization was the minimum possible, let's say that the goal of our flow was to get one thing, we wouldn't need anything more than the base network. And hence, the minimum utilization of the two together would just be 4. Right, we did this. We considered, well, if the base network is large enough that we can make a flow to hit the flow goal, we're done. It's at the minimum possible. If it's not big enough, the actual minimal utilization is not the same as the theoretical. So we should add more capacity somehow. Let's go to the whiteboard. Welcome back to the whiteboard. Think about the utilization. So UT of thingy network. Let's just call this load sigma, and that's a load function. So now what do we have? Well, so this is the maximum of load sigma A over WA. So we have this load, the weight, and this is of the original network. Now I'm going to do something a little strange, and I'm just going to put a little subscript S. Now you might be like, what are you doing that for? it's going to be useful to give that a different name than load B. Now, also let's go ahead and break up load sigma. Well, we have part of it's the flow, we'll just call that F, plus the load of the obstruction. Notice that NB is equal to, well, with some kind of residual, so we're subtracting the obstruction from NS, our original network, or as we'll learn of it, calling it the scaling network. But we kind of need to multiply it by something, and that something is the utilization of the obstruction on the original network. We should pause for a moment to think about why this would make sense. So take a quick look at what the values of this are. Let's see, the utilization of load obstruction over times NS, well, that's the maximum of load obstruction of an arc over WS of an arc. And let's take a look at let's look at arc alpha. We can see that whatever this thingy is, it's definitely greater than or equal to load at alpha over WS at alpha times WS alpha. We know that's the case because we're doing the maximum over A. If alpha is 1 where this thing is maximal, then this is equal. Otherwise, it's greater than or equal to. And we can very clearly cancel these out. What we get is that this combination is at least the load function at alpha. And that's what we need. We need node B to be greater than or equal to 0 everywhere and as small as possible. But let's think about something else. Also, I'm gonna give this thing a name real quick. I'm gonna say that this is K. So what I want to argue is that this equals K plus X. Now this X seems weird, it's not a variable I mentioned before. Let's call it the scaling parameter, but I'm gonna set X such that flow F, a flow on, I'm gonna say that it's a flow on X, NS plus NB. Oh, and let's drop a little therefore here. We're thinking to ourselves, wait, why does this work? Well, remember the concept of the residual. If we subtract a flow from a network, the network we get out, we can put flows on. Or this doesn't have to be a flow, it could be a load. And then if we add back the other thing, the thing that we remove to get the residual, we'd get something that works on it. So with that in mind, let's go over here and think about what this means. So since it's a flow on that, we can say F of A is less than or equal to XWS of A plus WB of A. Now remember what NB is. This becomes K times WS of A minus L obstruction at A. And that's by this definition up here. So we move this over. Now let's just go ahead and add load obstruction of A to both sides. So what we get is F at A plus the load obstruction at A is less than or equal to X plus K WS of A. This is looking very good because it's looking like this claim I made completely out of the blue. But now we can start to see where it comes from. Now let's divide it, both sides, by WS. We know it's positive. We're ignoring cases where WS might have zeros in it. And we also realize, hey, wait a minute, this is load sigma at A. So we get load sigma at A over WS at A is less than or equal to X plus K. Now, since this thing is always less than or equal to, there is a little caveat I have to put here. And no smaller X. If F is a flow of something with a smaller X, then this X isn't the same. The reason why we needed that is to make sure that this actually happens. But because that actually happens, we can take the maximum of it, of both sides, over all A. And well, the maximum of this is equal to, well, this is always constant for A. Because of the pink thing, this goes away and it becomes an equals. If that wasn't the case, then it would still be less than or equal to. But in the case where it is a flow on that thing and nothing smaller, then we have an answer. Now, why did we do this? Well, we know how to make max flows on a network, and in theory, we can compute max flows on a network. If I find an X that works, then that tells me that I found something that has utilization K plus X. So making this X smaller means that our result is smaller. So that's great. All right, hope you're ready. Hope you got all that. Let's continue. Let's put this all together. We flip the load into adding two networks together, as we saw at the end of the last whiteboard. And we have the base network and the scaling network. In the scaling network, we give it an arbitrary scaling variable X. And we could use max flow min cut in theory on this, and we'd get a function that shows how the value it is. And we get, for each cut set, the minimum of all of these little lines. And there's actually a structure to this that's useful. We obviously are not gonna compute the thing directly because the number of cut set for any real network is very large and very inefficient, but we can take advantage of a few tricks. First, we should talk about something that has been discussed in other videos before, but the bisection.